So I want you to keep in mind what you've learned in chapters 13 through 16 about addition to carbonyls, nucleophilic addition, and nucleophilic acyl substitution. We're coming back there, but in chapter 17 we take a detour to examine a new nucleophile. Oh, red, that's fun. And the new nucleophile, let's see, did I press record? Yeah. The new nucleophile is going to be called an enolate. So what is an enolate? Well, here is a carbonyl compound. And we've mentioned before that protons that are alpha to carbonyls are more acidic than a typical sp3 hybridized carbon-hydrogen bond. In fact, the pKa for a proton alpha to a carbonyl is around 20. And that should be somewhat surprising because a regular, well, maybe not that surprising, but a regular sp3 hybridized carbon-hydrogen bond has a pKa of like 50. So 10 to the 30 times more acidic. And the reason for that is, of course, that if a base removes the proton, the resulting conjugate base is resonance stabilized. So here is one resonance structure of the enolate, and here is the other resonance structure of the enolate. And you can draw the enolate either of those two ways. Those are two alternative ways of showing the enolate. What you need to infer by that is a couple of things. First, the pi bond is delocalized between the alpha carbon and the carbonyl carbon, and then the carbonyl carbon and the oxygen. And second, you need to infer that the negative charge is delocalized on both the carbonyl oxygen and the alpha carbon, both places, okay? In fact, you may remember, not sure, but you may get this from chapter, from your 351 experience on conjugation, resonance, and dienes. One of the ways we can represent enolate structure is by considering a pi system of molecular orbitals that are on each of these three atoms. So just to set this up briefly with the enolate, you should already be okay thinking about the carbonyl carbon and the carbonyl oxygen as basically being roughly sp2 hybridized, right? And that carbon-oxygen pi bond comes from what orbitals? What orbital on oxygen, what orbital on carbon? P orbitals, right? So we could draw a p orbital here with a lobe in the back with the, well, we'll use color another time, and then a p orbital here with a lobe in the back. And when they line up side by side, you have a pi bond. How about that adjacent atom, that adjacent alpha carbon? What is the hybridization of the adjacent alpha carbon? There's a little bit of controversy. Some of you were wanting to say sp3 because you look at that carbon and you're like, oh, it's got 4 things, including a lone pair. What is it over here? sp2. In resonance, do we change geometry? Do we hop back and forth, changing geometry? No. If it's sp2 here, it must be sp2 here. Has to be 100% of the time, no exceptions, right? And so what the resonance structures are telling you is that indeed that alpha carbon is sp2 hybridized, which must mean that the lone pair is in a p orbital, which can line up with the other 2 p orbitals. So we can create a pi system of molecular orbitals by mixing 3 p orbitals together to get what are going to be called 3 pi-type molecular orbitals out. And the process of mixing these together is just the maths of MO theory, and you don't have to worry about this. I will just show you what the results are. If we are looking down on this carbon oxygen pi bond, I'm just going to draw what the orbitals look like in this same sort of orientation. So the lowest energy orbital, which we will call pi 1, the one that is lowest in energy, you have oxygen here, carbon here, and the alpha carbon here. that lowest energy orbital is going to look like this. It's going to have a lobe above the plane of the page and then a lobe below the plane of the page. And we'll use color to represent a change in wave function sign. All right. And if you want to look at this thing from the side or imagine where it comes from, where do we get this from? You get this from having 3 p orbitals, one on carbon, one on oxygen, and one on the alpha carbon, line up adjacent to each other with the same wave function sign. So there's a couple of different ways we could draw that, but you understand where that one's coming from. The 3 p orbitals on alpha carbon, carbonyl carbon, and carbonyl oxygen, all lining up with each other with the same wave function sign. We get a single delocalized orbital, and that's the orbital that corresponds to these 2 electrons that are in the pi bond here and then in the pi bond there. This is the orbital that represents the electrons that are delocalized in the pi bond between carbon-oxygen and between carbon and carbon. The second one that we can get looks like this, and it corresponds to the lone pair that's on the oxygen and on the alpha carbon, but never on the carbonyl carbon. And that orbital looks like this. It has a lobe on the oxygen with another one below the plane of the page, and it has a lobe on the alpha carbon with another one below the plane of the page. And there is a change of wave function sign at the carbonyl carbon. There's a node that actually, we'll draw that in blue, that coincides with the carbonyl carbon. And if you were to view this from the side, what it would look like is a lobe on the oxygen and on the alpha carbon, but a node at the carbonyl carbon that's in the middle. How come you guys aren't clapping? Man, you're making me feel that. Thank you. There it is. Wow. I need an applause button, right? Yeah. It's a contest of fun. Okay. So the last highest energy orbital for this enolate looks like this. You have lobes on each of the carbons and a change of wave function sign in between each of the carbons, and we'll change color as appropriate to have. And if you were to draw this from the side, it would look like this. So maybe you've seen stuff like this before. It's hard to know, just depends on what you learned in 351. This highest energy pi 3 orbital has 2 nodes. And when looking at these pi type orbitals, it's easy to rank them in energy because you just count the nodes, or you count the number of times the wave function sign switches. In this orbital on the bottom, there are no nodes in between atoms. There is a node in the plane of the atoms, but there's no node in between the atoms, so that's the lowest energy one. The next energy one has 1 node, and the one higher than that has 2. So you can see that they're ranked in energy. The more nodes an orbital has, the higher in energy they are. The other thing to understand is this is not 3 orbitals side by side. This is 1 delocalized pi molecular orbital. A pair of electrons in this orbital spend their time above and below the plane of the page, hovering over all these atoms, oxygen, carbon, and alpha carbon. Whereas electrons in this pi 2 orbital simultaneously exist on oxygen and on alpha carbon, but they go to 0 at the carbonyl carbon. And then if you were to have electrons in this orbital, they would be on all 3 atoms, but they would go through 0 in between the atoms. Now, with that orbital picture in place, we can, and we've ranked the orbitals in energy, we can decide which ones are filled and which ones are empty. The question we want to answer is how many electrons are involved in pi bonds plus adjacent lone pairs. And the answer is 4. 4 in the lone pair here, and 2 in the lone pair here, and 2 in this carbon-oxygen pi bond, or alternatively, 2 in the lone pair here and 2 in this carbon-carbon pi bond. So we fill the lowest energy orbital and then the next one up. And what this tells us, the MO picture is complementary to the resonance picture. Notice that the highest energy electrons in the MO picture are the ones that are delocalized on the oxygen and on the alpha carbon, but never on the carbonyl carbon. And notice that that's what resonance tells us too. The lone pair is only ever on the carbonyl oxygen and on the alpha carbon, never on the carbonyl carbon. And notice that the lowest energy electrons involved in resonance are the ones that are delocalized across alpha, carbonyl carbon, and oxygen. And notice that the electrons in this pi bond are between carbon and alpha carbon are also in the pi bond between carbon and oxygen. What I'm trying to tell you is the purple electrons in the resonance structure above are these ones, and the pink electrons are those ones. Okay, questions? Questions about that picture? Yeah.
So you're saying there's 4 electrons in these orbitals?
4 electrons, 2 in each orbital. Yeah.
But the ones in the lone pair never are on the carbonyl carbon?
Never on the carbonyl carbon. Yep. All right, so this is a MO picture of resonance. We'll come back to something like this in the future when we talk about resonance in benzene rings. But for now, the idea that the enolate is resonance stabilized is good enough. Okay, so this pKa is high enough, though, that you expect the enolate to be relatively nucleophilic. That's a higher pKa than the pKa for, say, an alcohol. So an enolate should be more nucleophilic than an alkoxide. And so we will use the enolate as a strong nucleophile. Now, resonance tells you that the enolate is the HOMO of the enolate. Remember, when we think about the nucleophile, we are worried about the highest energy electrons. The HOMO of the enolate nucleophile is this pi2 orbital, which is on both oxygen and carbon. So we're going to worry a little bit about whether the enolate uses the lone pair on the oxygen or the lone pair on the carbon. It's the same lone pair, but whether that lone pair attacks from the oxygen or the carbon. What we're going to see for the most part is that enolates will be reactive on the carbon. The reason for that is that oxygen is more electronegative than carbon. So we will see, like we saw in carbonyl chemistry, this pi1 orbital, the lowest energy electrons, this one leans toward oxygen. So if we were to actually draw what this orbital looked like, probably if you have oxygen here, carbonyl carbon, and alpha carbon here, probably this lowest energy orbital leans somewhat towards the more electronegative atom, which is oxygen. And correspondingly, we will see that the higher energy orbital, the pi2, is going to lean toward the alpha carbon to sort of compensate for the leaning of the pi1 orbital towards oxygen. So it will turn out, if you wanted to imagine what this pi2 orbital, the HOMO, actually looked like, it's probably a little bit bigger on the alpha carbon than it is on the oxygen. So I'll draw a smaller lobe there. And that's a result that comes from the math of MO theory, but it's important because it's an insight that leads you a little bit different place than you might have otherwise come to. And let me explain that just a little bit. Some of you are going to look at these two resonance structures and you're going to say, this one here on the right with the negatively charged oxygen is a better resonance structure than the one on the left with the negatively charged carbon. Because you will say oxygen's more electronegative than carbon. And you're right. that this is probably a major contributor. Nevertheless, experimentally, we observed that enolates don't react on the oxygen very much. Instead, they react on the alpha carbon. Two rationales for that. One is that the HOMO is mostly on the alpha carbon, and the other rationale for that is, in the end, carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds, so it's a more stable outcome for the enolate to react on the alpha carbon to keep the carbon-oxygen pi bond intact. Okay? But the punchline is, for all of this, is enolates are nucleophiles, and even though the HOMO is both on the carbonyl oxygen and the alpha carbon, they are mostly reactive on the alpha carbon. Which is great because that means we can use enolates to make carbon-carbon bonds. So before we do some examples of that, what we want to spend a little bit of time on is just thinking about the different types of enolates. And it turns out that, and their relative reactivity, and it turns out that everything you've learned so far about carbonyl compound reactivity, you can use to rank the acidity of alpha protons and also the stability of the enolate. Okay? So, for example, yeah, that's fine. One of the most reactive carbonyl compounds we encountered was the aldehyde, right? That was one of the several that were at the top of our list. And actually, I want to just, for fun, we'll put the hydrogen here, we'll put the alpha carbon here. And I'll write pKa here, and then we'll draw the enolate conjugate base. The pKa of an aldehyde is around 17. So that's not much less acidic than an alcohol. And of course, we'll draw the enolate conjugate base. We may not draw all of the enolate conjugate bases because you'll get the point pretty quickly. Next is the ketone. We said that the ketone was slightly less electrophilic than the aldehyde because alkyl groups, like a CH3 group, can donate electron density into the carbonyl carbon, and you'll notice actually that the ketone is less acidic than the aldehyde. Oops, unless we draw it exactly the same way, which would be silly. The ketone is less acidic than the aldehyde by a factor of about 1,000. Okay, how can we rationalize that? Why do you think that's true? Go ahead.
So is it because the methyl group is kind of doing a little bit of hyperconjugation with the carbonyl carbon? And so therefore it's not going to be pulling on the alpha carbon?
Okay. So you're saying that you expect this methyl group, because this is an electron donor via what we've talked about before, hyperconjugation. You're saying electron donation should do something to the ability of this carbonyl to stabilize the negative charge? Sure, okay. Can we expand on that a little bit? Why should electron donation here mess with what's going on here? Let's draw the other resonance structure just so we can have a place to talk about it. Notice that the thing that stabilizes the negative charge on the alpha carbon is the ability of the carbon-oxygen pi bond to move up and become a negative charge on this oxygen. And also, realize that we could draw a third resonance structure for this system that would look like this, with a positive charge on the carbonyl carbon like this. In other words, we expect that electron-poor carbon-oxygen pi bonds should be better at stabilizing the negative charge on the alpha carbon. So the more electron-poor the carbonyl carbon is, the better it's able to accept electron density from that alpha carbon to do this resonance structure. Does that make sense? So another way to think about it is if you've got an electron donating group here, that's going to destabilize the negative charge. And you've thought about things like that in Chapter 2 of 351 as you thought about inductive effects. Electron donating group should destabilize this conjugate base. And so, tell me, what do you predict for an ester? Where should I put the ester? Do you think the ester is going to be more or less acidic than the ketone? Is the ester more or less reactive than the ketone? Less, because of the electron donating OR group, right? We can draw that for the ester. It looks like this, and lone pairs on that adjacent oxygen actually donate electron density by resonance into the carbonyl carbon. That should make the carbonyl carbon less electrophilic, and indeed the ester's pKa is 100,000 times less acidic. Okay, and so you can continue. Amides should be even less acidic. So we won't actually do, this is mostly academic, we won't actually make enolates in any of the examples we're going to talk about in this class out of amides. And the reason is their pKa is so high. Why? Because the amide nitrogen is a really good electron donor. And that makes the amide carbonyl carbon even less electron poor, which means the conjugate base of the amide is not as stabilized. Okay, go ahead.
So then, if I'm understanding this correctly, if we were to say put on the ketone or the ester on the side, put like a chloride or a halogen of some sort, it would increase the acidity of it?
Sure. So if you were to imagine, sorry, where are you thinking about putting groups?
Sorry, let's just start with the ketone.
Okay.
Where the methyl is.
Yeah, you could imagine if you start putting electron withdrawing groups here, it might lower this pKa a little bit. Yep. If you put the electron withdrawing groups on the alpha carbon, that would have an even bigger effect. So let me show you an example of that. One of the ways you can make aldehydes and ketones even more acidic is to put an additional electron withdrawing group on the alpha carbon. So I'm going to create a separate category for these. I'm going to call these beta dicarbonyl compounds for reasons that will become clear in a moment. Imagine you take the ketone, and here's the alpha carbon. But then on that alpha carbon, you stick another carbonyl. So here's a carbonyl carbon, here's the alpha carbon, oops, and here's the beta carbon. That's why we call it a beta dicarbonyl compound, because you have two carbonyls and they're each beta to each other. It turns out the pKa for that proton in between the two ketones is 9. So that's actually astonishingly low for an sp3 hybridized carbon-hydrogen bond. That's more acidic than an alcohol. That's even more acidic than an ammonium ion, than a nitrogen attached to 4 protons. That's something that you could totally and completely deprotonate even with hydroxide. And of course, the reason for that is, let's look at the conjugate base. In the conjugate base, notice that the negatively charged alpha carbon can be resonance stabilized by delocalization not just to the carbonyl on the left, but also to the carbonyl on the right. So you, except if you don't draw it right. So you have an additional place that the lone pair can delocalize to. If we highlight in pink places that the lone pair can be, it can be on those alternating atoms. So we'll see that beta dicarbonyl compounds are especially acidic, and it turns out you can mix and match these, and they're among aldehydes, ketones, esters, and their pKa's actually follow sensible trends. For example, make a prediction here. What if I replace one of the ketone groups with an ester? What do you predict here? Should it be more acidic? Should the alpha proton be more acidic or less acidic than the diketone? Less, right? Because esters are less good at withdrawing. Esters are less electron poor, and it's electron poor carbonyls that do the better job at stabilizing conjugate bases. And indeed, the pKa for an ester is, again, about 10,000 times less acidic. If you do, that should be 11, so it's about 100 times less acidic there. If you do the diester, it gets even less acidic, but still more acidic than if you just had one carbonyl. So the pKa of this beta diester is around 13. Now these aren't numbers for you to memorize, but they are trends for you to be aware of and to be able to use and predict. The other reason we're talking about this is we're going to think a lot when we make enolates about what kind of base we have to use to deprotonate an alpha carbon. And we're going to make a choice, sometimes based on desired outcome, sometimes based on cost, about what base we want to use. And the basic question, yeah, that's a funny pun. 2 out of 10 for a dad joke there. The basic question we're going to ask is this base that we're going to use strong enough to completely deprotonate the carbonyl compound to give us the enolate, or will we get an equilibrating mixture of enolate and starting material? And that's going to have some consequences. Before we do that, questions? Yeah.
You were just put in a quick sentence the pattern for which drawing groups, what would you use?
The pattern for...
The drawing groups raising the
Oh, okay. The pattern is, if we're thinking about not the alpha carbon, but the thing on the other side, better electron donors make the pKa higher, makes the alpha proton less acidic. And the best electron donors are atoms that have high energy lone pairs that can donate into the carbonyl carbon by resonance. The beta dicarbonyl compounds are related to that. The more, for the reasons I showed you here, if you have a second carbonyl, the pKa drops down tremendously because you're able to delocalize the lone pair electrons on the alpha carbon in more places, but not all adjacent carbonyls are equal, so more electron poor adjacent carbonyls give you a lower pKa. And adjacent carbonyls with good electron donors don't move the number as much. Okay, others? All right, so let's dive into how we form enolates. There are going to be two sort of strategies for forming enolates, and one is what I will call reversible or equilibrating enolate formation. And this is where you use a base that's not strong enough to completely deprotonate your enolate. That is, you use a base that's only going to generate a very small amount of enolate. Now, why would you ever do this? A couple of reasons. First, less reactive bases are generally cheaper and easier to work with. Second, sometimes in chemistry you don't need a very large amount of a nucleophile to get a reaction going. And third, you're going to see that the reaction outcome will sometimes be different if you use a less reactive base. So we'll get to the rationale and examples in just a little bit, but for now, let's show you an example of how you can make an enolate under reversible conditions. So we'll start with a ketone, and the alpha proton on the ketone, as I've said above, and you don't need to memorize this number, you could look it up, I have it in my notes, so I'm looking it up, is 20. And suppose I react this enolate with hydroxide, and react this carbonyl compound, this ketone, with hydroxide, and the resulting enolate will be this one. I'm going to choose, because enolates react generally on the alpha carbon, I'm going to choose to draw the enolate resonance structure like this. Your text will most often not do that. Your text prefers the enolate resonance structure where the pi bonds between carbon and alpha carbon and the negative charge is on the oxygen. Either is totally fine. You can do whatever you want. In any case, that's the enolate. And then the other product is water. The pKa of water is 16. So you tell me, this is now a 351 question, which side of the equation dominates at equilibrium? The left. You guys are pointing that direction. Stage whatever, right? Yeah, okay, got it. Stage right, stage left. I don't know which is which, who cares? This way, right? We all agree on that way. Good, and in fact, it's about a ratio of 99.99% starting material and less than 0.01% of enolate. That's okay, because that's actually enough to start reactions and to get things going. Now, that will have some consequences a little bit later on, and let me illustrate that with an example carbonyl compound. Here is a related ketone, and this ketone has two different kinds of alpha protons. Alpha proton in orange and alpha proton in purple. Okay? And I'm going to use hydroxide as my base. And if I deprotonate on the alpha carbon, on the purple alpha carbon, I'm going to get the following enolate. Which looks like this, and I'm actually going to draw the other enolate resonance structure. If I deprotonate on orange alpha carbon, I get this enolate. And I will also draw its resonance structure, which looks like this. All right, so I've got two different possibilities. Now, before we consider which possibility is going to lead to, which possibility is more favorable, let's just think overall about what we said above, for this example above here. If the enolate is present in such a small ratio, what does that tell you about the energy of this enolate relative to these starting materials? Is it higher or lower in energy than the starting materials? Higher, much higher in energy, right? So if we were to draw an energy diagram, we'd have starting materials down here and enolate would be way up here. Right? Okay, so let's actually make this sort of realistic. We'll draw an energy diagram where we go from starting carbonyl compound and hydroxide to enolate and then water. both of these enolates are going to be higher in energy than the starting material for sure. What about the relative stability of the enolates? Can you think of anything you've learned before that might help you decide whether or if one of these enolates is more stable than the other? Go ahead. Zaitsev rule, which was, sorry, sometimes I don't remember the names of dead people, so that sounded like an insult. It wasn't. That's the one about more substituted alkenes in E2 reactions. I think that was it, right? Okay, what did you learn about more substituted alkenes? They're more stable, right? You maybe just memorized the rule. The actual reason for that is probably also hyperconjugation. More alkyl groups have more adjacent CH bonds, which can hyperconjugate into the carbon-carbon pi star. So yeah, we're going to use that principle from 351, which was that more substituted alkenes are more stable. Applying that here, we will say that the purple enolate, by virtue of being more substituted, that is more alkyl groups, is more stable. Whereas the orange enolate is less substituted and is therefore less stable. Now, both of those two enolates are themselves still higher in energy and less stable than starting material, but the purple enolate should be a little bit lower than the orange enolate. So, oops, didn't circle everything. So we'll draw our energy diagram this way. We'll put the energy level of the purple orange enolate there. We'll put the energy level of the purple enolate there. I don't actually know about what the actual numbers are, so we're just being qualitative in this. But what we mean is that this starting material has to go uphill less to get to the purple enolate than it has to go uphill to get to the orange enolate. Which means that under these equilibrating conditions, there should be more of the more substituted enolate. Which means that our major product is going to come from the more substituted enolate when we make the enolate under equilibrating conditions. All we're talking about so far is how we prepare for a reaction by making the enolate nucleophile. And I'm telling you, when you make the enolate under reversible conditions, where you only make a very small percentage of it, your product is going to come mostly from the more substituted enolate because there's simply more of that present. Okay? All right, questions about that? Again, we haven't even said what the nucleophile is going to be attacking. That would be another step where we draw an energy diagram going downhill to products. But we're saying that more of the products are going to come from this nucleophile because there's simply more of it present. All right, that's an important point. The second conditions that we're going to run the reaction under are conditions where we make 100% of the enolate. This is going to involve irreversible enolate formation. What that basically means is we're going to use a base that is strong enough to give us 100% yield of the enolate. So there's multiple ways you can do this, and it's just about using a base whose pKa is higher than the pKa of the alpha proton you want to remove. For example, here's an example of irreversible enolate formation. I have a carbonyl compound that has two different kinds of alpha protons. The ones that are alpha to just one carbonyl should have a pKa of around 20. The ones that are alpha to two carbonyls, as we've said for the beta diketone, I think that pKa was like 9. So if I use my base being hydroxide, and then I draw the enolate on this side and then the conjugate acid of my base, which of the two protons that I've highlighted, we can use color again, let's use purple and orange. Which of the two alpha protons, purple or orange, gets removed? Orange, easy. The most acidic protons get removed, period. Okay? So that means the enolate we get is, I guess we'll draw this here, we get exclusively the orange enolate. And tell me about yield. Let's look at the pKa of the conjugate acid, which is 16. Which side dominates at equilibrium? The right? The strongest acid loses its proton. This is a factor of 10 to the 7. So that's 99.999999, maybe 7 nines, something like that. I probably got that wrong, but basically we'll just scribble that out and write 100%. Okay? Meaning that, and it's irreversible, meaning that you can't go backwards because the equilibrium constant is so huge that there's not even any of the starting material left. Okay? Another example is to use a base that is so super strong that it can deprotonate even a carbonyl that's even an alpha proton that's not in between two carbonyls. So we'll go back to just a plain old ketone, pKa 20. And we're going to introduce a base that is a nitrogen base. It's got 2 isopropyl groups on it, and the counter ion is lithium. This is the base LDA, which stands for lithium. That's the L, diisopropyl. And then the functional group that has an alkyl nitrogen with a negative charge on it is called an amide or amide. So lithium diisopropyl amide, that's different from the carbonyl functional group amide, but they've used the same term for both of them, so whatever. That is a base that has a conjugate acid whose pKa is actually pretty high. The conjugate acid has a pKa of 38, maybe actually 40. It's even less acidic than that. So that means that, again, in over 100% yield, you make the enolate and you can't go backwards. Okay? Now, why would you ever make a partial amount of enolate? Well, LDA is kind of expensive, and it's so basic that you can't use protic solvent. You got to use some of the same kinds of solvents that your text has used before for Grignard reagents or organolithium reagents. Whereas if I do reversible enolate formation, I've got hydroxide and water around anyway, so protic solvents are not a big deal. So there is an expense issue for why you would want to use LDA. There's a second issue for why you'd want to use LDA. And remember what we just talked about. When you make the enolate under reversible conditions, the reaction is selective for the more substituted enolate. There's a word we should introduce at this stage because you have a starting material that could react in a couple of places. The word, when you get preferential reaction at one of two options, is called regioselective, where regio means a different region of the molecule is reacting. So reversible enolate formation conditions are regioselective for the more substituted enolate. For irreversible conditions, that regioselectivity switches. You will see for our starting material that we just barely introduced with the the orange enolate and the purple enolate. For LDA, you will see that we exclusively get, or we get with some regioselectivity, the less substituted enolate. So LDA is regioselective for the less substituted enolate. And the reason for that is sterics. The less substituted enolate is less sterically hindered, and therefore it forms faster. And in a reaction that's irreversible, what forms faster is the major product always, because you can't go backwards once you form it. What we basically mean by this is that the barrier to enolate formation is higher for the purple enolate than for the orange enolate. So the orange enolate forms faster. Okay? So you can see why we'd want to use LDA if we want to use the less substituted enolate. You can see why we'd use reversible enolate formation if we want to use the most substituted enolate. Okay, that's it for today. Good luck on the exam. I'll see you Wednesday.